So this is just a continuation of where the last video broke off. What I was saying is that I have an external magnetic field that's pointing away from us, and I've got an electron being shot into the field. So since it's an electron, I'll use my left hand. The magnetic field is pointing away from us into the board. So when I take my hand, I've got to make sure my fingers are pointing into the board. The electron is traveling that way. So I'll rotate my hand, still keeping my fingers pointing the same direction so that my thumb is pointing to the right. And what I get is that I'm pushing down on the electron. So if you think about what would happen then to the electron as it would enter the magnetic field, this region of the magnetic field, is that it would curve downwards like that. Now we got to be careful here because this is the direction of its path, right? That's showing where it would go. If the question was simply saying what's the direction of the force, I would say arrow pointing down labeled FM. Those are two different questions. If the question said what's the direction of the force and you drew the path, it wouldn't be right. Same way that if I asked for the path and you drew FM, again, it wouldn't be right. What we got to do is answer the question that's being asked. The really neat trick about this, though, is that because we got the electron to start to curve downwards, at first sight, it basically looks like projectile motion. And in fact, if this kind of got out of the field, then that's all it would be. But in the next section of notes, where I show some things that we can do now that we have these formulas and ways of doing the hand rules, I show something we can do to trap a charged particle like this when it's going through the field. And it's the idea that if I can get it as it curves down to get it to stay within the boundaries of the magnetic field, I can trap it. So make sure that you check in the next section of notes how I explain that could happen.